Right, so continuing with the finite element solution of the heat transfer problem in 2D. This is part B of lecture 17. In part A, let me just do the brief recap of the end of part A, which was the definition of the stiffness matrix and the force vectors. So if you recall, we had once we have the weak form of the heat transfer problem in 2D, and then we have the way to discretize functions and get gradients of functions in terms of the shape functions of the element. Then we put that into the weak form, and what we end up with is the definition of the element stiffness matrix, which is the integral over the domain of the element of this BE transpose matrix times the conductivity matrix times BE over the element. And this BE matrix is a matrix that has the gradients of the shape functions. So it has dn1 dx, dn1 dy, dn2 dx, dn2 dy, and so on. So that's the definition of the stiffness matrix, and then we also defined the force vectors. So the force vector coming from the source term is going to be an integral also over the domain of a vector with the shape functions of the element times the source term integrated over the domain. The source term is a scalar. So this n E vector is just a vector with all the shape functions, n1e, n2e, and so on. And then finally, the force vector corresponding to the flux term would be the integral over the boundary of the element that is part of the boundary with natural boundary conditions. So only boundary with natural boundary conditions, and then we integrate the vector of the shape functions times the value of the flux over that part of the boundary. But this is only going to be non-zero whenever an element has an edge on part of the boundary that has a natural boundary condition. Otherwise it will be zero. And then, so that's the definition of the element stiffness matrix, element force vector from the source, and the element force vector from the flux. And then the assembly is pretty much the same as we've done before. So to illustrate that, what we're going to do is we're going to do one example. I should say, let me backtrack a little bit for a sec. So what does this look like? As you can see, this definition is independent of the element that you choose. But for example, if you choose the linear triangular elements, then this B matrix, which is 2 times the number of nodes per element, then becomes 2 by 3. This is a vector of the size number of nodes per element. So in the case of the linear triangular element, this has 3 entries. So for the 3-node triangular element, we can define the shape functions either in terms of the xi eta space or in terms of the xy space. So for this particular example that I'm gonna do, because it's convenient, we can have the shape functions directly in terms of x and y, as you can see here. So these are functions of x and y. So we don't need the isoparametric map. The gradient of a shape function can be calculated directly. The B matrix, you can calculate the derivatives of these shape functions directly with respect to x and y. And if you do that, then you'll see that the B matrix for the triangular element is a constant. So for linear triangular element, BE is constant. and it's given by this. It just depends on the nodal xy coordinates. And that's pretty much all we need. So let's do one example. We're gonna do example 8.1 from the book. We have a domain that has two flux boundary conditions. So you can see that the top part of the domain has a boundary condition of a flux of 20, and then the other one has a flux of 0, and then essential boundary conditions on this edge and this edge. So we're gonna do first is we're gonna discretize this into the nodes and the elements. We're gonna use two triangular elements. Maybe I'll use different colors. So this will be node 1, this will be node 2, and this will be node 3, and this will be node 4. Similar to what we were doing in 1D, you should number the nodes such that the essential boundary conditions are numbered first. So in this case, because we know that the essential boundary condition is temperature equals 0 on this edge right here, therefore that's why I numbered this node and this node first. And then instead of numbering this node, because this one doesn't have essential boundary condition, I actually went here because this edge also has an essential boundary condition. So that's why I number first these nodes 1, 2, 3, and then at the end I numbered the element which has a natural boundary condition, which is this one. So those are the nodes, and then just to have the mesh, I'm going to split the mesh like this. So this will be my element 1, and this will be my element 2. And this is arbitrary, you could do some different mesh, but this is the mesh that I'm deciding to do. So that will be my first step, is going to define the mesh. So you can see I number the nodes, I have the elements, I'm just gonna write my element connectivity. So element, because it's triangular mesh, every element is made out of 3 nodes. So element 1 is made out of nodes 1, 2, and 3. And remember this is just a notation, but a little bit more than notation. It guarantees that the Jacobian is going to be positive. I didn't really explain that, but always do counterclockwise numbering of the nodes. So element 2 is going to be made out of nodes 2, 4, and 3. So that will be my mesh. That's the first step. Then I'm gonna do the same thing that we would do in 1D, for example. Once you have the mesh, the second thing that you would do would be for each element get KE and then assemble into global stiffness matrix. So we begin with element 1. Let me just redraw the element 1 here. So element 1 looks like this. This is local node number 1, local node number 2, local node number 3. And I'll just write the global node numbers. In this case, they coincide. So this is local node, and in red I have the global node number. So you can see that I need the local node numbers because I need to know what x1, y1, x2, y2, x3, and y3 are, and those depend on the local node number. So x1, the coordinates of the first node of the element are just 0, 0. Then x2 and y2 are 2, 0.5, and then the node 3 is 0, 1. So those are the coordinates of my element. given these coordinates, I can assemble the B matrix for element 1. And I have it calculated already. That is just going to be 1 over 2 times the area of the element, which is 1 in this case, times minus 0.5, 1, minus 0.5, minus 2, 0, and 2. And this looks like magic, but all I did was I used this definition right here, and then I just plug in the values of x1, y1, x2, y2, etc. So if you do that, then this is what you get for the B matrix of element 1. So the stiffness matrix of element 1 is going to be the integral over the triangle of this B matrix transpose times the D matrix, which I'll bring up in a sec, times the B matrix of element 1 integrated over the triangle. And then let me just say, so this D matrix is given in the example, so this is just K times the identity. So actually the multiplication by the identity just gives the same result, so we can get that out of the way and just use the value of K, which is 5. So in reality this is 5 times the identity, so I can get rid of that matrix here. So I'm just gonna leave the 5 times B1 transpose times B1 d omega. So we need to integrate this over the triangle, but note that the B is a constant, so this B matrix is a constant, so I can take it out of the integral, and then what I'm gonna end up with is just 5 B1 transpose B1 integral of d omega, and this is just the area of the triangle. So the element stiffness matrix is just going to be 5 times the area of the triangle, which in this case is 1, times, so B1 transpose B1. And note that the B1 matrix is a 2 by 3 matrix, so when you transpose that and multiply by the other 2 by 3 matrix, you're gonna get a 3 by 3 matrix. And I have it here already, so I'm just gonna write it down because there's no point in doing the calculation in the video. So this will be 5.3125 minus 6.625 minus 4.6875, then 1.25 minus 0.625 and 5.3125. And this is a symmetric matrix, so I just need those values, then the rest I can fill in by looking. So that is the stiffness matrix for element 1. So now we need to assemble this into the global stiffness matrix, and for that I need the global known numbers. So if I go back to my numbering, the global known numbers are 1, 2, and 3. In this case they coincide with the local known numbers. So I can have my K1 tilde, which is going to be, this is the global, the contribution of the first element to the global stiffness matrix. The global stiffness matrix has size, total number of nodes. So this one will be 4x4 matrix. Should say this is the assembly step. So in this case, because the nodes coincide, I'm pretty much gonna get the exact same thing. So I'm not gonna write the whole thing. So I'm gonna skip some decimals here. So that's the assembly is in this case easy because the numbers are 1, 2, 3. So you can see that this guy goes right here. So this is the exact same thing that we have done before. I think it will be a little bit clearer with the second element. So that's the assembly of the first one. Now for the second element, again I'm gonna redraw the element right here. The element looks like this. So this is the second element. And then in this case, you can see that the local node numbers and the global node numbers don't coincide. So the local node numbers are 1, 2, and 3, but the global node numbers are 2, 4, and 3. If I did it correctly, yes, 2, 4, and 3. So based on the local node numbers, I could have x1, y1, x2, y2, x3, and y3. So first one will be x1, y1, which is this node over here, and that one has coordinates 2, 0.5. So 2, 0.5. Then the second node for this element is this node right here, so the top corner, and that one has coordinates 2, 1. So 2, 1. And the third node of the element is this one right here, and that one has coordinates 0, 1. 0, 1. So now, given the x and y coordinates for this element, I can assemble my, well, this is not assembly, I can put together this B matrix for the second element. And again, I'm gonna skip the details, but scrolling back up to the definition, again, I'm just gonna use this directly, use the area of this triangle and the xy coordinates of this triangle, and I have calculated it before. So I can tell you that in this case, the B matrix is 0, 0.5, minus 0.5, minus 2, 2, and 0. So given the B matrix, I also need to calculate the stiffness matrix for this element. Then this is again the integral over the element of B to transpose times the conductivity matrix times B2 integrated over the element. But like I said, this is the D matrix is the identity multiplied by K, and then the B matrix are B matrices are constant. So I can just get K times B2 transpose times B2, and then the integral of the d omega. This just gives me the area of the second triangle. And if you do the multiplication of the B2 transpose times the B2 and you plug in the value of K, what you will end up with is that the K2 is going to be a 3×3 matrix, because it should be the number of nodes per element times the number of nodes per element. And in this case, I calculated ahead of time. This is 10 minus 10, 0. Then 10.625 minus 0.625, and then 0.625, and it's symmetric, so I just have minus 10, 0, minus 0.625. And I need to assemble this into the global stiffness matrix, so let me just make this a little bit more compact. Assemble into K2 tilde. And K2 tilde is going to be, because this is the contribution to the global stiffness matrix, this is going to be size total number of nodes, so 4 times total number of nodes. And in this case, here I need to write the global node numbers. And you'll see that in this case, they are not the same as for the first element. So what I have right here is 2, 4, and 3. And that's in that order, because that's how I numbered my element. I numbered it like this, right? Starting from here, then this one, then the one on the top left. So here I just do the same: 2, 4, 3, 2, 4, 3. So for example, this entry should go to the entry 2, 2. So that would be here. Then these entries right here go to 2, 4, and 4, 2. So 2, 4, and 4, 2. Then this one right here is going to be going to 4, 4. So 4, 4 is right here. 10.625. Then let me do this one. So that was 4, 3. So 4, 3 right here minus 0.625, and 3, 4 minus 0.625. And finally, this one, which is 3, 3. So that one is 0.625. And the rest is zeros. So 1 with everything is zeros, and then the 2, 3 entries are 0. So you can see that in this case, things actually got a little bit shuffled. So that's pretty much what I need in order to get the full stiffness matrix. I have the contribution from the first element, I have the contribution from the second element. So the total K matrix is going to be the K1 tilde plus the K2 tilde, and it's going to be a 4×4 matrix. Which I have right here. So this is 5.31 minus 0.625 minus 4.68, 0. I'm only gonna do the upper right That's it. And then it's symmetric, so I don't need to put it. So that's my global stiffness matrix. Now, what about the force vectors? Let's do, let me see, what number am I using here? So force vector due to source term. And again, we need to do this for every element. So for element 1, this one will be integral over the element of the first shape function times the source term, integral of n2 times the source term, integral of n3 times the source term. And in general, you would have to do this integral, which might be a little bit complicated. So if, for example, if the source term is some nonlinear function, then you have to do the integral, and then doing the integral in the xy space is a little bit complicated. So instead, you would have to use the isoparametric map and define the parent domain triangle with hexaeta coordinates. But we're not going to do that because the source term is a constant. So in this case, because the source term is a constant, I can just take it out of the integrals. So I'm just going to completely take it out of the picture, and I'm going to end up with integral of shape function 1, integral of shape function 2, and integral of shape function 3. And that you can actually do without computing the integral if you remember for any given triangle. Say we have a triangle that looks like this, where this is local node number 1, local node number 2, and local node number 3. Shape function 1 is a function that is 1 at node 1 and then goes to 0 for the other 2 nodes. And the integral of shape function 1 over the triangle is actually nothing more than the area of the triangle over 3. Just believe me with that one. And that's the same also for shape function 2 and shape function 3. So actually, in this case, when the source term is a constant, you basically have constant times the area of the triangle over 3 and a vector of 1s, 1, 1, 1. So this is true because S is a constant. But that's what we are going to do in this class, so it's fine. And then we want to assemble this. Again, we need the global node numbers, so 1, 2, and 3 for this element. So we have our global vector fs. Let me call it fs1 tilde. And that one is size of total number of nodes. So that one is 1, 2, 3, 4. So you can see here that I'm gonna have S A1 over 3, S A1 over 3, S A1 over 3, 0. So as the source force vector from element 1 and the corresponding assembly, then for element 2, fs2, s is also constant for element 2, so this will just be the same. I won't redo it. This is just s times the area of the second element divided by 3 times 1, 1, 1. And then for the assembly, again, list the global node numbers. So the global numbers is 2, 4, and 3. for this element. So we can do the assembly into the big fs2 tilde vector, which is size 4. So in this case, you can see that 1 will end up empty, and then here we end up with SA2 over 3, SA2 over 3, and SA2 over 3. But the order would be not necessarily, it's a little bit shuffled. So this one goes here, and this one goes here. So the total force vector due to the source term is just going to be the F1 tilde plus the F2 tilde. So that one's just going to be SA1 over 3. Here SA1 over 3 plus SA2 over 3. Here again SA1 over 3 plus SA2 over 3, and here just SA2 over 3. So that is my global force vector corresponding to the source term. We're almost there. The one that we are missing is the force vector due to the external fluxes. That one is a little bit trickier because that one requires, if you remember the expression of the integral, so let's do for element 1. This will be F1Q. And the definition that we introduced before was integral over gamma q of n times q bar d gamma. So only this integral needs to be done only on boundary with natural boundary condition. So if you look at element 1, I need to scroll all the way up, but if you look at element 1, for element 1, none of the edges of the triangle have natural boundary condition. This is the first edge, doesn't have a natural boundary condition. This is the second edge, also doesn't have, it's an internal edge, so no natural boundary condition. And then if you look at this edge, also doesn't have natural boundary condition. So none of the edges of this triangle have natural boundary conditions. So for element 1, actually all these integrals are 0. So for element 1, you just get 0, 0, 0. So for element 1, no edges have natural boundary condition. What happens for element 2? Again, the definition is the same. So FQ for element 2 is going to be the integral over gamma q of NE times q bar d gamma. So for element 2, we can see that this edge, so the first edge of the triangle has a flux, but it's a flux equal to 0. And the second edge right here also has a flux, which is non-zero, it's 20. So actually that one we have to integrate. And then the last edge, the edge right here, that's an internal edge, so that one won't have natural boundary conditions. So really it's only the second edge that has flux. So that's the only one that we need to integrate. let me just redraw that triangle here. So for the second element, this was the local node number 1, local node number 2, local node number 3. Global node numbers were 2, 4, and 3. And in terms of which edges have flux, this one has a flux of 20. And actually that's the only one that we care about, because the other one has a flux. So this other one right here has a flux, but it's a flux of 0. So you can see that when you integrate that one, you will get 0. So we don't really care about that one. The only one we care about is the top edge. So what happens with this edge? Which are the shape functions that are non-zero over this edge? So what this will be, so this FQ2 is going to be only, I'm just going to put in words, it's going to be the integral over the top edge of the shape functions times the Q bar. We have 3 shape functions, so I'm going to have a vector of 3, where this one is again integral over top edge of n1 times Q bar, then integral only over top edge of n2 times Q bar, and then integral over top edge of n3 times Q bar. And again, I should have here another integral over right edge of n1e times the other Q bar. Maybe I should say 1 and 2. So this will be one of the Q bars, and here I would have the other one of the Q bars. But the thing is, as I said, this other Q bar is 0, so this whole part of the vector will just be 0. So let me just, this is 0 because Q2 bar equals 0. So really the only one that we need to care about is this one. And again, if the Q was not a constant, then you would actually have to do the integral over the top edge, so a line integral. But Q is constant over the edge, so I can also just take that out. So I'm gonna get FQ2 is just gonna be the Q2 bar, which is the 20, times integral over top edge of n1, integral over top edge of n2, integral over the top edge of n3. And we'll do some magic here. So which shape functions are non-zero over that edge? So if you look at the, let me redraw this thing again one more time. So this is the element. This is the local node number 1, local node number 2, local node number 3. So the first shape function, n1, should be 1 at this node and should go to 0 at the other 2 nodes. So it turns out that this shape function is 0 over this edge. Therefore, this one is going to be 0. Then I'm going to redraw the element one more time. So this is local node number 1, local node number 2, local node number 3. And so for the second element, N2 is 1 at node 2, and it goes to 0 at the other two nodes. But in particular, I want to integrate N2 over this edge. So what I care about is I care about this triangle right here. And what I can tell you is that the integral of N2 over top edge is just going to be the length of that edge over 2, because that's the integral of that triangle. So length of edge over 2. And finally, let me just do, so this one will be length of the edge over 2. And let me do it for the last one. So again, local node number 1, local node number 2, local node number 3. So N3 is a function that is 1 for node 3, and it goes to 0 for the other two nodes. But I only care about what is the integral over this edge. And so I only care about this triangle right here, and then the integral over the edge of N3 is actually also the length of the edge over 2. So this is also length of the edge over 2. So finally, FQ of element 2 is going to be Q bar, which is 20 times first shape function is 0 over the top edge, and then for the other two is just length of the edge, which is 2 over 2, so I'm just going to end up with 1. And then assemble into the global so I have my F2Q tilde, which is the size of the total number of nodes. 1, 2, 3, 4. And I have 0, 0, 20, 20. I didn't do the assembly for the first one because it's zeros, so it doesn't matter. So I just left the local F1. I didn't do the assembly, but it doesn't matter. In this case, I have the local force vector, and here is the assembly into the global force vector. All right, so now I finished. I have the global stiffness matrix and the global force vectors, both the source term and the flux term. So I can just set up my system of equations. And I think that's step number 5. System of equations is just K times the degrees of freedom equals Fs minus Fq plus reactions. So the K, I can just try to copy. Let me just copy. So that times the value of the temperature at node 1, temperature at node 2, temperature at node 3, temperature at node 4 equals the force related to the source term, which is this guy right here. I actually have calculated the numbers ahead of time. So let me just copy that. So that is 2331. I calculated that already, and then minus the flux term, and that one is just 0, 0, 2020. That's this guy right here. Plus the reactions, and that one is basically the nodes that have a fixed value for the temperature should have a reaction, so should have an extra flux. So the first 3 nodes are the ones that are on the essential boundary. We just scroll back for one last time just to show that this, and these nodes have a value of temperature that is fixed, so they will have some reaction flux. So that is my global system of equations. Again, this is the K, the value of the temperature, the force term due to the source, the force term due to the flux, and then the reaction fluxes. And I know this one I can replace. This T1, T2, T3 are going to be 0. So how do I solve this? I can do the matrix partitioning. Just like before, we have 3 nodes that have a known temperature, so I could just split everything based on those 3 essential boundary conditions. So this is NE equals 3. I have 3 nodes that have essential boundary conditions, so I could use that to split the system, and then I will end up with an equation for T4. And if you solve that, you get that it is minus 1.788 Celsius. So that's it. That's the example for lecture 17. And I also have code that I will upload and has exact same solution but in code. And